Okay, everyone, so I wanted to go over linear interpolation because this was where a couple of students, well, more than a couple, kind of got stuck on the test. And so I just wanted to kind of do a dedicated video to this since you will be using this the rest of the semester, and it'll be really easy for you to just pull this right back up if you're having any questions. So, first of all, what is linear interpolation? I didn't go this deep into it because I know that you've had this in your prerequisite classes, but for me to understand something and remember it, I really need to understand kind of everything about it. So, linear interpolation, its sole purpose is to fill in the gaps, right? So we'll just do fill in the gaps or holes in tables. So this is what it's designed to do. So you know that when we are looking at the tables and we're going off of let's say, the temperature, well, it can't give us a value for V and U and, all of this other data on every single temperature out there, right? So it could give us at 20 degrees Celsius, but it can't give us 20.1. It can't give us 20.125. It can't give us, there's an infinite amount of numbers with corresponding data that they would need to give us to cover all of it for us to not need a set of rules or an equation that would enable us to find whatever we need in between. So what they do is they make the tables like we have, and maybe they're in, 10 degrees Celsius increments or 5 or 20 or whatever table you're using. But so say you're needing to find a temperature between 20 degrees and 40 degrees, because that's what the table's given you, right? Maybe it goes 0 degrees Celsius, 20 degrees Celsius, 40 degrees Celsius, 60 degrees Celsius, and you have that corresponding data. But what you actually need is 30 degrees Celsius or 25 degrees Celsius. And you go to the table and you say, whoa, that's not on there. But I know that I'm at the right table, right? But they don't have a value for that. That's where we use linear interpolation. That's where we can use this set of this equation and these set of rules to pick up and find the data that we need. And so I hope that that kind of helps you understand why we need linear interpolation. And it's really to fill in the gaps or holes in tables pretty much across the board. And we use it here. So I want to go over, because you guys are just coming off of exam 1, it's going to be problem 3 and within that question B, where we are going to go over the linear interpolation. So I've seen this done a couple of different ways on the exam. Number 1, the student knows that they're at the right table. They know that they're at the right information, and they know that they need to linear interpolate. But for some reason, whether they ran out of time or test anxiety kind of got the better of you, that you just kind of got tripped up and just skipped it and didn't have time to come back and finish it. So that's scenario 1 that I've seen. And then scenario 2 is the student comes to the right table, right, and has the right data, and it comes time for them to linear interpolate, but their value, maybe their temperature, that they're going off of, or their pressure that they're going off of is not there. And then they second guess that they're at the right table at all. Or they put in between, because they know that they should be doing something, but, not enough time, you're under the crunch, and so you can't really delve into that. And so then again, you just skip it and you miss it. Well, as you can tell, this is there's an A, B, C, D, E, F, G. I've got my notes right here, all the way to H. And everything passed B except for, I think, one or maybe two questions depends on this linear interpolation. So everything builds on it. So a lot of the students that skipped over this also had to skip over about 4 or 5 more questions past that because they didn't have this data. Okay, so that's what I'm going to go over. And I know that you have the test still, so be sure to reference this if you have any questions. What I did notice is that everyone is doing a really good job of, just about everyone is doing a really good job of using the flow chart to get to the right table, right? So we're going through this, this question. We know that we are at a superheated vapor. We have found that on the flow chart, so we've gone through the steps of assume a two-phase mixture. We've gone down and we've done the comparison to T is greater than T sat. Well, what do we have? We have a superheated vapor. Well, now we still need that data, right? Because that's why we're using the tables. We're going to the tables to pick up the things like specific volume or internal energy, specific internal energy, things like that. So that's why we first assumed the two-phase mixture. We went down there, found out, actually, hey, our data is not matching. We are not at the right table. What table do we need to go to? That's when we go to the flow chart. We go through the flow chart questions. We end up at superheated vapor. So now we know what we have, and now we know what table to go to. So we go to that table A4. I have it up. So here is A4. See properties of superheated water vapor. And so then we scroll down, and it's at a pressure of 3. So here's our pressure of 3. And our temperature that we're given is 300. Okay. So what we see over here is that we're not given a 300 temperature right here. We're given a 280 and a 320. And so this is where I'm saying the two scenarios of the students come up. Either the first student knows that he's at the right table. He says, hey, I am supposed to be at table A4. I am supposed to be at pressure 3 bar, and I'm supposed to be looking for temperature of 300. It is not here, and I'm not really sure how to get there, how to get these values. These values right here, let's pull up and see this. VUH and S that you can get from here. So he says, I know I'm at the right table. I know I'm at the right pressure, but my 300 is not here, and I'm just going to move on and come back. Okay, so you have that situation. And then you have the other student who comes down here and he says, well, I think I'm supposed to be at A4. I mean, that's what the flow chart said, and I've been doing that right. And I know that the pressure is 3 bar, but I don't have a temperature of 300. So I must have just done something wrong to get here, and I must need to go to a different table. Okay, so both of those are wrong. What we need is when we don't have our data explicitly spelled out for us, like 280, right? 280 has all the data that we could need. 320 has all of the data that we can need. And we know that our temperature right here is in the middle. So what can we do? We can come up here and we can use linear interpolation to fill in the gaps or the holes in the tables, right? So everything in between 200 and 240 is a gap. Everything in between 280 and 320 is a gap. We happen to be looking for 300. So our 300 is within the gap of 280 and 320. So we are going to use the values from 280 and 320 to get the data for 300. And it's going to be accurate. And because there's infinite number of temperatures within this gap, that's why they can't explicitly tell us every single temperature within there that we could ever need. Okay, so what I do is I set up my problem the exact same way. every single time I linear interpolate. And the reason why I do that is because it makes it very easy to use the formula. So right now, what I'm trying to find is specific volume. And I'm trying to find specific volume at a temperature of 300 degrees Celsius. So I'm going to go and put down my temperature because that's what I'm using to find specific volume. So I've got 3 T's, right? And I want you to think about this. Put your middle T as what you're looking for. Sorry, because this is the middle gap that we're trying to find. So 300, literally saying the wrong thing as I write it. Okay. 300 degrees Celsius is what we're trying to find. And we know that from our table, because we just said it, that 300 degrees is located in between 280 and 320. So 280 is going to be our lower limit, and 320 is going to be our upper limit. The closer that you can box in this hole, the better. So you've got 280. That's our lower limit. And then you've got 320, which is our upper limit. Okay, now what are we trying to find? We're trying to find specific volume at 300 degrees Celsius. This is what we're trying to find, right? This is a question mark. This is what we're looking for. Okay, but what we have is this data right here. We can get this and we can get this. So let's go ahead and get that. Okay. V equals, and then we can come back down here to our table and pick these up. So remember, stay at your pressure. We've got a 280, specific volume at 280 degrees Celsius is 0.844. And a specific volume at 320 is 0.907. Okay, so let's go ahead and put those in here. 0.844 meters cubed kilogram. And then 320 is 0.907 meters cubed kilogram. Okay, and so then from this, we can get our data. Okay, and so on your formula sheet, you have 3 different forms of linear interpolation. Y equals mx plus b, that's just the line. What we concentrate, and really it's just depending on what you're looking at, what we use for this is this long one down here, the y equals y1 plus y2 minus y1, x2 minus x1, x minus x1, okay? So this is what we end up using in the formula. We're going to use this formula right here. Okay, and so that formula the reason why we use this one is because we can first of all use the data that we have to get our y, which is this v, but also because when you set it up like this, and you always set it up with your lower limit at the top and what you're trying to find in the middle and your upper limit at the bottom, then it's going to become very easy for you to just plug in your numbers without having to think, well, what's my y and what's my x and all of that. 1. Okay, so that's our formula. Let me just make this bigger now. Okay. Okay, so now let's use green. So if you're having trouble remembering what is your y and what is your x, you are looking, this is what we're trying to find right here. It's the only thing with a question mark. And this equation is set up for that. So if you ever forget, just remember that what you're looking for is your y. So this is your y column, and this is your x column. So temperature is going to serve as your x, and specific volume is going to serve as your y. So we have our x and y column. Now what are these? So this first column is going to be 1, your subscript 1, and then this column right here is going to be your subscript 2, and then this column right here is going to be like nothing written down, right? Okay, that looks like I'll just put nothing. Or you know what, I'll just put no subscript. Okay, that might help out. So like here, this is no subscript, and here, this is no subscript. So that makes sense, right? Because the formula is y equals, and this y doesn't have a subscript, and this column doesn't. So let's just plug in. We've got y that we don't know equals y1, so 0.844, plus y2 minus y1, all of that over x2, so we're going to go up to x2 is 320, minus x1, which is 280, and then that is all multiplied by x, no subscript, so here's our x, no subscript, 300, minus x1, which is 280. And then again, what you would do first is you would just subtract these, subtract this within the parentheses, and then, your just order of operations. But what you end up with is y equals 0.8755 3. Let me just start that over. What you end up with is y equals 0.8755 meters cubed kilogram. And remember that your y, right here, your y no subscript, y no subscript is v. So v equals 0.8755 meters cubed kilogram. And you can put a subscript here to denote the state. And what we are doing is working on state 1 in this problem. So I'm just going to put a 1. So this is your answer. Okay, I hope that helped. Please let me know if I skipped anything or if something was confusing, and I'll be happy to help.